In this video, I'll talk about the most common fragmentations of alkyl halides and possibly how you actually really recognize in a mass spectrum that actually contains a chlorine and bromine. Having a chlorine and bromine and identifying those mass spectrum is actually relatively easier. It's not as easy with the fluorine and iodine, but chlorine and bromine is relatively easier. There's two reasons. There's one reason. In case of chlorine, you have two isotopes where chlorine um, 35 and you have chlorine 37. And turns out that the chlorine 35 is about roughly 67% and chlorine 37 is about roughly 33% most abundant. And then when I'm looking at bromine, you have bromine 79 and you have bromine 81 as two isotopes. And they're almost 50-50. I would say, I think 79 is about 51% and bromine 81 is about 49%. So they're roughly 50-50%. So you see the molar mass here is actually between those chlorine 35, 37, and bromine 79 and 81 has a difference of 2. So you see a significant M plus 2 peaks in these guys right there. So you would have M plus 2 radical cation peaks for these guys, and no other halogens or no other atoms really shows that M plus 2 significance peak. Now, how do you really differentiate between the chlorine and bromine? In case of chlorine, your M plus 2 peak is going to be roughly 1/4 of the M plus peak. And then in case of this one, so this one would have been the bromine, that would have been M plus radical cation here, and this would have been M plus 2 radical cation. And they're almost going to be 50-50%. And why they're 50-50%? Because their relative abundance is almost 50-50. So let's look at this graph right here. On this mass spec, if you look here, I got a molar mass of 100 and it's 100. That's 110. It seems like it's 110 and it's 109, 108 and 110. So if you have 110, just do the math here. If you have 110, I'm going to subtract 81, so that gives you 29, so that makes sense. So this is actually an ethyl bromide. So I have 3 lone pairs on the bromine. I'm going to go ahead and make a radical cation out of that. When I make the radical cation, I can say that one of the electron goes away from the bromine because bromine has a bunch of non-bonding electron pairs, and one electron kind of gives you that radical character. So I could draw this electron here, that's why I've drawn as in the radical form outside the molecule, or I could leave this electron right on the bromine, so it doesn't really matter, but it would still give you a positive charge. So this right here, the M over Z for this would be 110. Well, 110 and 108. So 108 would be coming from bromine 79 and 110 would be coming from bromine 81. Now, since they are almost 50-50 in their isotopic ratios, that's why you see this M plus peak and M plus 2 peak there. So this one is an M radical cation signal, and this one is an M plus 2 radical cation signal. So they're almost 50-50%. That's how you know that you actually have a bromine present in there. Now, one of the most common fragmentations that these alkyl halides do, and that applies to chlorines and iodine as well, that you can actually go ahead and break up the halogen, carbon and halogen bond. So when you go ahead and break up the carbon-halogen bond, suppose, I'm going to break it up right there, we typically get a bromine radical. So this is bromine radical, and I'm going to get an ethyl carbocation here. So this is either going to be 79 or 81, and when I get the M over Z for this cation, that would have been, let's say if I go for 81, that would have been 110 minus 81, that gives you 29. So then I go back and check if I have anything at 29, and turns out we do have this right there at 29, and that happens to be the base peak because it's 100%. So that's really the most common fragmentations that you would see in case of an alkyl halide. But then remember, you can also recognize the presence of especially the chlorine and bromine within an M+2 radical cation peak. Suppose if I have a chlorine, like how does that differentiate between the chlorine and bromine? And I have this mass spectrum here, which is in chlorobenzene here. And again, I can be like, all right, I got multiple electrons on the chlorine. Those are non-bonding. So I want to go ahead and lose an electron to make a radical cation. I can lose an electron from the non-bonding of the chlorine. So that leaves one electron back on the chlorine. So that gets you a positive charge and one electron kind of lost. So M over Z for this one. Okay, so that is actually going to be C6H5. That's 77 in chlorine there. So that would be 77 plus 35. Is that 112? So we got 77 plus 35. That's 112. So this is going to be at 112 and 114. So I do see this one right there that's at 112, which is going to be M plus the radical cation, molecular radical cation peak. And then you also have an M+2 signal there, M+2 radical cation. So that would be at 114. So know the difference. So here the peak is almost like 1/4, technically you can say, or like almost more than 1/3 in terms of height compared to this guy right there. That you would not see typically in case of a bromine, because in bromine it's almost going to be 50-50%. So again, it happens to be the molecular ion peak happens to be the base peak as well, because this is actually 100%. But let's see what other fragmentation that you can see possibly here. And like I have said, one of the most common fragmentations that you would see in case of halogens is obviously the breaking of the carbon-halogen bond. So if I go ahead and break the bond right here, I'll end up getting a chlorine radical, and I'll get a carbocation here. So when I get a carbocation here, this actually get an M over Z of 77. This is not very stable. It's not like the same as benzylic cation. So because remember, the benzylic cation would have been very stable. That would have a mass of 91. This one you can see a little bit, and if you see something around 77, kind of gives you an idea that there must be an aromatic in this particular mass spectrum, or in this particular structure here. So you see this right there, that's an M over Z of 77. So that's coming from this phenyl carbocation here.